Okay, hello and welcome back, everyone. So we're going to continue talking about the Weierstrass representation. And let's sum up what we know so far. So we have the following equivalent formulations for a minimal immersion with isothermal coordinates. So here, the domain D is some domain in the complex plane. So the first equivalent formulation is that the coordinate functions are harmonic. The second is if I form the vector phi, which is d psi du1 minus I d psi du2. Then this vector phi satisfies that it's holomorphic. And the sum of the square of the components is equal to 0. Right. So if I break down what these two properties tell you, this is what tells you that I have a minimal surface. And this is what tells you that is that I have isothermal coordinates. And the third equivalent way we talked about last time is I can write phi of the complex coordinate z. So here, z I should think of as u1 plus iu2 is the real part of a line integral from 0 to z of the vector I get by taking 1/2 f 1 minus g squared I over 2 f 1 plus g squared f g. All of this evaluated at the point zeta d zeta, and then I have to take the real part of that whole thing. And here f is holomorphic. G is meromorphic. Meromorphic. And if G has a pole at Z0 of order M, then F has a 0 of order at least 2M at Z0. So we have these three equivalent ways to formulate this, and we investigated some consequences of this. So this these two functions f and g, so some notation we established last time. F and g are the Weierstrass data associated to the surface psi d. So we also discovered, we also saw that G is equal to the inverse of stereographic projection. Composed with the normal map. So in this way, we see that the condition that I have a minimal surface implies that the normal map, the Gauss map, if I consider the normal map as a mapping from this domain D in the complex plane into the Riemann sphere, which is CP1, this is a holomorphic map. Okay, so that kind of summarizes most of where we were. Right. So the next thing I want to talk about is a little bit of a sideline in something called the Schwarz reflection. So I want to recall something for complex functions. So if I have if I can decompose the boundary of my domain into two parts where let's call them, here I might have gamma 1, and here I might have gamma 2. And the property I want is that gamma 1 lies in the real axis. So what are the hypotheses? I want D to be a function from the closure of this domain to the complex plane. I want it to be holomorphic on the interior. I want it to extend continuously, at least to this blue part of the boundary, but let's extend it continuously to the whole boundary. And the final thing I want is that and F restricted to this blue part of the boundary is contained in the real axis. So under all these hypotheses, basically what I have is that F is holomorphic to one side of this domain. And then the part of the domain contained in a line gets sent to another line. That's really all I need. If the part of the domain were contained in a circular arc, I can send it to a circular arc. That's really all I need. I need the mapping sends one line to another line. And after rotations, I can arrange these lines to be horizontal. Right. So then I can extend okay, so let's look at what we have here. Let's go back to our picture. We have D to one side here. And I'm going to just mirror this domain D to the other side of this blue curve to obtain this green part. And then for any point down here in this green part, I'm going to say that the value of F at this point, this is for the D star. For any point down here in this green part, I'm going to say that the value of the point in this green part is the complex conjugate of F at Z bar. So I reflect across this line, and then I have to take the complex conjugate of the function value at that point. So the consequence of this is that now I've defined a function on this new domain. This is now a nice domain in the complex plane, and this extension is holomorphic. And you can check the Cauchy-Riemann equations. To verify this is indeed a nice holomorphic function. Okay. Right. So what is the main takeaway? So I can reformulate this to say that if F maps a line to another line, I can extend it across this line holomorphically by complex conjugation. Okay, so what does this have to do with our minimal surfaces? So I remember, back to minimal surfaces. So we see that our minimal surface is determined by, so the minimal surface, this is given by a triple phi1, phi2, phi3 of holomorphic functions. Which satisfy the condition that phi1 squared plus phi2 squared plus phi3 squared equals 0. Right. So if I have such a triple of functions, so I have my phi mapping D to really C3. It's not defined as above, and I write boundary of this domain as gamma 1 union gamma 2 and phi of gamma 1 is contained in a straight line. Then I can extend phi by complex conjugation. What does this do to the surface? This says that if the boundary of my surface contains a line, then I can extend my surface by rotating about this line. L by the angle of pi. Right, so let's maybe draw a picture. If I happen to have a minimal surface here, so let's draw our minimal surface. Like that. And this part of the boundary is in a straight line. So here's my minimal surface. This part of the boundary what can I do? I can continue this surface by rotating the whole surface 180 degrees. I rotate about the line L through an angle of pi, 180 degrees, and I get an analytic continuation of the surface. Okay. Now, what's the next thing we can do? We'd like to generalize this a little bit. And let's remember that the coordinate functions are harmonic functions. Okay, but what is one thing I can always do, at least on a simply connected domain, with a harmonic function? I can always construct the harmonic conjugates. And the harmonic conjugates are exactly the functions satisfying the Cauchy-Riemann equations. So here are my nice Cauchy-Riemann equations. Right. And on a simply connected domain, the harmonicity of psi is exactly the condition saying that I can locally at least solve these PDEs. And so it's worthwhile to think about, what does this do? So geometrically, this rotates the gradient by an angle of pi in its tangent plane. So you can see the fact that it's a rotation by pi clearly from this from these formula. The fact that it stays within this tangent plane, we're going to see in just a second. So to see that, let's remember that the relationship between phi and psi. So the associated, okay, so what do we have? We have the conjugate harmonic functions. The conjugate harmonic functions will then define a new minimal surface called the conjugate minimal surface. These conjugate harmonic functions define a new minimal surface called the conjugate. Okay, and as always, the conjugate harmonic functions are well-defined up to adding a constant, which means that the conjugate minimal surface is well-defined up to a translation. So there's always this ambiguity of translating back and forth. Okay, let's unravel what this tells you a little bit. We can write down phi tilde is, of course, d psi tilde du1 minus I d psi tilde du2. But then using my Cauchy-Riemann equations I had up here, this is minus d psi du2 minus I d psi du1, which is then minus I times d psi du1 minus I d psi du2, which is minus I phi. So these phi's are related by this very simple looking relationship. And now I can write down the Weierstrass representation data of the conjugate minimal surface. So I have the phi's in terms of the Weierstrass representation are given by a half f1 minus g squared I over 2 f1 plus g squared fg. And remember, this is, oh, there's be tildes here everywhere. Remember, this is supposed to be minus I phi, which is minus I times a half f1 minus g squared I over 2 f times 1 plus g squared fg. So what does this mean? This means that I can take f tilde is minus I f and g tilde is g. And this is kind of the important observation. The normal maps agree. So the fact that the normal maps agree means that the tangent planes themselves are the same. Within this tangent plane, the difference between the two immersions is a rotation by 90 degrees. Okay. So here's maybe another picture. I have my domain D in the complex plane. It's mapped down to two ways. It's mapped down by psi and psi tilde. And here, I have two surfaces. If I pick a point, say this point here, I'll see that the normal maps to these two surfaces are the same. Okay. Back in my domain, I can choose a curve. Here, let's call this curve C. And this curve can get sent down to the curve gamma in this and it can get sent to this curve here. Let's call this curve maybe beta is psi tilde, or let's call it gamma tilde is psi tilde compose C. And how are these two curves related? Well, back in this picture, I had a tangent here and a conormal. Let's get sent to a tangent and a conormal, and a tangent and a conormal. And what do I see in these pictures? I see that the difference between the two curves gamma and gamma tilde is that the tangent to gamma is the conormal to gamma tilde, and the tangent to gamma tilde is the conormal minus the conormal to gamma. And this swapping, this fact that I've essentially swapped the tangent to the curve and the conormal to the curve. So let's just remember that the conormal to the curve is tangent to the surface, but perpendicular to the curve. The fact that I'm swapping this tangent to the curve, the tangents and the conormals to the two curves, this is a consequence of the fact that the Weierstrass, the conjugate functions, the act of taking the harmonic conjugate is a 90-degree rotation, a rotation by pi over 2 in the tangent plane. Okay, so what do we see? So I combine this. With my reflection principle. See the following. If the boundary of my minimal surface is gamma 1 union gamma 2, where gamma 1 is planar, constant conormal. A curve is planar precisely when it has a constant conormal. Then I can extend my surface by reflecting across this plane. And this whole idea is exactly what's called the combination of these two is exactly what's called the Schwarz reflection principle for minimal surfaces. So let's draw a picture. If I have my minimal surface, if the boundary of my minimal surface is contained in a plane, I can extend this minimal surface I can extend this minimal surface by reflecting. Okay. So we've seen that if the boundary of our minimal surface either contains a planar curve or a line segment, I can extend my minimal surface either by reflecting across the plane or rotating by 180 degrees around the line. So in fact, the Schwarz reflection principle is a little bit stronger than that. In fact, if my minimal surface contains a line segment, then it must be invariant under rotation by an angle of pi about this segment. Let's go ahead and prove this. Let's draw my surface. Maybe my surface looks something like that. This is my minimal surface. And let's suppose it contains, let's suppose it contains this blue line. So what do? I decompose my surface into two halves, the part on one side of the line. Let's call this part psi plus, and let's call this part psi minus, and what do I know? I know that if I define psi hat is equal to psi plus to one side of L, and the rotation through an angle pi of psi plus to the other side of L, this is a minimal surface. In isothermal coordinates. Okay, so what does this mean? This means that the coordinate functions are harmonic. But psi hat is equal to my original psi on an open set. And harmonic functions satisfy the unique continuation property. So since these two harmonic functions agree on an open set, they must agree everywhere. That completes the proof. And obviously you have the same statement for planar curves. Similarly, let's just write it this way. If psi of D contains a planar curve, then psi is invariant under the reflection through this plane. Okay. So let's examine this through the example of the catenoid and the helical. So two surfaces we know, so we know the catenoid and the helical. So we know that the catenoid is a surface of revolution. And since the catenoid is a surface of revolution, any profile curve is planar. All the profile curves are planar. Okay, so if I draw my catenoid like this, I see I have two planar curves here and here. So these are two planar curves. with conormal plus or minus, well, in this case, is going to be the vector sticking out of the page. So here, let's draw some orientation. So this is the x3 axis. Right. So the conormal of these curves, this conormal points down into the page. It's going to be minus E1. And this conormal for this guy here is going to be plus E1. If I look at the conjugate surface, I see that the two conjugate curves, I'm going to have one curve with a conormal equal with a tangent equal to minus E1, and one with a tangent equal to plus E1. In between, I'm going to have all these other curves. So for instance, this curve here, this curve here, those are all curves that, those curves also all have constant conormal, and the conormal swings between minus E1 and plus E1. So I see that then what do I get? I get the conjugate surface being ruled by lines. So the conjugate surface is ruled by lines. Let's try to draw a picture this way. So if I rotate my picture a little bit, I'll have and then in between, it's going to twist around like that. So this is really one way to see that the conjugate surface to a catenoid must in fact be the helicoid, because so what do we know? We know that the catenoid, we've already seen that the catenoid is the only rotationally invariant minimal surface other than the plane. And similarly, the helicoid is the only minimal surface other than the plane ruled by lines. So this is ruled. Other than the flat plane, it's the only minimal surface ruled by lines. So whatever the conjugate surface to a catenoid is, it has to be a minimal surface ruled by lines. we also know that the normal vector, the Gauss map to the catenoid is non-constant, but the Gauss map to a flat plane is constant. And the two Gauss maps of these surfaces must agree. Therefore, the only possibility is that the conjugate surface to the catenoid is indeed the helicoid. So other than going through and solving these equations, this is a very nice geometric way to see these two, how these two surfaces must be related. Okay, so I'd like to close with one slight generalization and talk about the whole associate family. And how do I want to talk about this? So I want you to remember that the conjugate harmonic functions, we obtain conjugate harmonic functions after rotating the derivative of psi by an angle of pi over 2. Sorry. Let's rewrite this again. D psi du1 is cosine pi over 2 d psi du1 minus sine pi over 2 d psi du2 and d psi tilde du2 is sine pi over 2 d psi du1 plus cosine pi over 2 d psi du2. Right. Yeah, so if I just plug in the values for cosine of pi over 2 and sine of pi over 2, I recover the Cauchy-Riemann equation. But there's actually nothing particularly special about this angle of pi over 2. I can do the same thing for any angle alpha. So I can define d psi tilde du1 is cosine alpha d psi du1 minus sine alpha d psi du2 and d psi tilde du2 is sine alpha d psi du1 plus cosine alpha d psi du2. And I can do this for any angle alpha. And again, the harmonicity. So is the integrability condition. I can always, at least locally, solve these PDEs precisely when the original size harmonic. The harmonicity is exactly the integrability condition, which is the same as checking the equality of mixed partials. So if I trace through, if I go through the same sort of computation, I'll find that my phi tilde is e to the minus I alpha phi. I have this very nice relationship between the associated holomorphic functions. And then if I write down the Weierstrass data, for the associated family, I find e to the minus I alpha times f g. So I can summarize this by saying that I have not just one minimal surface, not just one minimal surface and its conjugate. I have actually a whole family of minimal surfaces parameterized by an angle alpha. And these minimal surfaces are given in terms of my data. So F, remember, is a holomorphic function. G is a meromorphic function. Satisfy this condition on the zeros and poles. And I see that the Weierstrass representation of the whole associated family is given by this very nice formula. And I can see very explicitly where the angle comes into this parameterization of the whole family. Okay, so this completes the discussion of the various reflection principles, Schwarz reflection principles, and conjugate harmonic functions and conjugate minimal surfaces and this whole associated family. And we will continue with a further discussion of the geometry of the Gauss map and some of what that means next time.